thanks everyone for coming. So today we're really happy to have Andrei Rapinchuk speaking about groups with bounded generation, old and new.
Thank you very much for the invitation, and in fact for the opportunity to discuss one of my favorite topics, groups with bounded generation. So let's go straight to the definition. So an abstract group gamma is said to have bounded generation property if there is a finite collection of elements in it, not necessarily distinct, such that the group itself can be written as a product of the cyclic subgroups generated by those elements. This definition has an obvious profinite version, namely, a profinite group gamma has bounded generation in the profinite sense if, again, one can find a finite collection of elements in it, not necessarily distinct, so that the group itself is the product of the closures of the cyclic subgroups generated by those elements. Clearly, if a group gamma has bounded generation as a discrete group, its profinite completion has bounded generation as a profinite group. Now, the question of whether the converse is true remained open for quite some time, and the results that I'm going to talk about in this presentation actually show that bounded generation in the profinite sense does not imply bounded generation for the discrete group. And one can view this as some kind of indication that, in fact, in some situations, profinite bounded generation may be even more useful than discrete bounded generation. And I will get to this in the end of my talk, but in the major part of the talk, we'll be talking only about bounded generation for discrete groups. Also, while bounded generation is obviously a purely group theoretic property, as we will see in this talk, both positive and negative results of bounded generation have very strong number theoretic connection. And this, at least to some extent, justifies my giving this talk in the number theory seminar. So let me start with some remarks and examples. Obviously, every group with bounded generation is finitely generated. Conversely, every finitely generated abelian group, or more generally nilpotent group, has bounded generation. Also, there is a theorem of Maltsev that states that every solvable subgroup of G and Z is actually polycyclic. And this tells us that solvable subgroups of G and Z all have bounded generation. Now, in all other situations, verification of bounded generation is quite non-trivial, as we will see later. But I must say that the first semi-simple examples like SL and Z, where n is at least 3, came about even before the formal definition of bounded generation was given, as a consequence of investigation of a natural question in linear algebra. Namely, suppose we have a unimodular matrix over a field. Then we can run the Gaussian elimination algorithm on this matrix to reduce it to the identity matrix by a sequence of elementary row or column operations, which of course results in the presentation of my matrix as a product of elementary matrices. Now, what's important for me here is that the number of steps that the Gaussian algorithm requires is bounded by a constant of the magnitude n squared plus change. In particular, it's independent of the matrix A. Now, you can do reduction not only over the field, but also, let's say, over Z. Using long division process or Euclidean algorithm, one can also reduce every matrix, every unimodular matrix over Z to the identity matrix by a sequence of integral elementary operations, which of course results in a representation of my matrix as a product of elementary matrices with integer entries. But then we can ask the same question. Can the number of steps be bounded by a constant, which of course should depend on n, but which is independent of the matrix itself? And for n equals 2, the answer turns out to be negative. And the underlying reason is, of course, the fact that SL2Z is a virtually free group. And free groups do not have bounded generation. But what about the case when n is at least 3? This question was asked by Dennis and van der Kallen in 1979 over any ring of algebraic integers. And soon after it was asked, it was actually answered in the affirmative by the following theorem of my colleagues at Virginia, former colleagues Carter and Kallen in 1983. So the theorem is as follows. So let O be a ring of algebraic integers. They also have this result for S integers, but with a slightly weaker bound. Then every matrix, every univocal matrix over O is a product of at most this number of elementary matrices. Of course, as you see, the bound is independent of the matrix, and it's weakly dependent on the field. So here we have delta, which is the number of prime divisors of the discriminant of K. And I will get to this again on the next slide. Now, this, again, purely linear algebra theorem results in a bounded factorization of our group SL and O as a product of cyclic subgroups where all generating elements are unipotent. Now, the case of SL2 over the ring of S integers turned out to be a bit tougher. And in fact, it was completely resolved only relatively recently. Well, of course, when O is Z, or in fact, the ring of integers of an imaginary quadratic field, again, gamma fails to have bounded generation. And the reason over Z is the fact that SL2Z is a virtually free group. The reason over the ring of integers of an imaginary quadratic field is similar. Namely, in this case, SL2 is known to virtually have a non-abelian free quotient, which doesn't have bounded generation. Now, all other cases were covered in the following theorem, proved jointly with my former student Morgan and Suri. And it states the following. So suppose the group of units of our ring is infinite, where O is again the ring of S integers of some number field. Then every unimodular matrix is a product of at most 9 elementary matrices. And of course, one application of this theorem is that the bound I had on the previous slide can be made independent of the field over all fields except for imaginary quadratic extensions. And this result has a mini history of its own. In fact, it first was observed by Cook and Wimberger in 1975 that the required assertion can be derived with a bound 5 instead of 9, assuming a certain form of the generalized Riemann hypothesis, which allows us to make certain conclusions about Artin's primitive root conjecture. Okay, of course, the generalized Riemann hypothesis remains unproven. So the next step was done by Dave Morris, who in 2007 reworked the old preprint of Carter, Keller, and Page, where they proved the existence of a bound using model theory. So in addition to some non-trivial model theory, this work also relies on the stronger version of Vinogradov's result on Goldbach's conjecture. And no explicit bound can actually be derived from the proof, or at least has not been derived from the proof.
But it's not because of the Goldbach is effective. That's not the reason.
That's not the reason. So the reason is model theory.
Okay, fine.
Now, Maxim Semirnov in 2014 proved this assertion, again with the bound 5, using some results of his Brown on the Artin's primitive root conjecture. So in some sense, it was a return to the original work of Cook and Wimberger. Now, our proof uses only traditional algebraic number theory, so meaning basically Chebotarev's density theorem and some computations with power residue symbols. And I should mention some work which was not put up on this slide. So before our work, there was a work of Leal where he proved the assertion for certain number fields, but this class of number fields did not include actually the rationals. Then there was a work of Kumar Murthy where he proved the assertion if we localize sufficiently many primes. This result didn't cover, for example, z of 1 over p. Also, there was a follow-up work by Bruce Jordan and Eugene Zeitman, where they, under certain assumptions, improved the bound of 9 to 8. Now, my student Morgan said that he could actually improve the bound to 7 in all cases, but I haven't seen his proof yet. Also, Jordan and Zeitman gave some applications of this theorem to other questions. But the point that I want to make is that this theorem gives a bounded factorization for SL2, where some elements are unipotent and some elements are semi-simple, with unipotent elements always present. Now, bounded generation is known also for many other S-arithmetic subgroups of isotropic algebraic groups over number fields. Now, in 1990, Tarkin proved bounded generation for all Chevalier groups of rank greater than 1, and for many quasi-split groups, with the group SU21 still being a notable exception. Now, in my work with my student Yarovenko, so we considered isotropic but not necessarily split or quasi-split orthogonal groups, proving bounded generation for this. And my other student considered also some unitary groups. So in other words, there has been some activity around bounded generation that from time to time would produce new examples. But the general case of isotropic groups still remains open. But
you have higher rank here, is it higher gamma rank? I mean, do you need unipotence?
Yes, well, first of all, we need positive rank, and then we need the S rank to be at least 2.
Okay, S rank. Mm-hmm.
So why are we interested in groups with bounded generation after all? So it turns out that this very simple-minded condition of bounded generation has rather strong properties for the group itself and also its representations. So let me mention some of these consequences. One has to do with so-called SS rigidity. We say that a group is SS rigid if it has only finitely many equivalence classes of completely reducible representations, let's say complex representations in each dimension. Another way to think about these groups is to say, well, if gamma is finitely generated, then one can define the corresponding character variety. And then SS rigid groups are precisely those for which this variety is 0-dimensional in all dimensions. Now, the traditional examples of such groups are, of course, higher rank lattices in Lie groups, and that condition for them is derived from Margulis' superrigidity theorem. But some time ago, I was able to formulate sort of an abstract version of SS rigidity, namely, if our group gamma has bounded generation and satisfies the following condition that Bess coined FAB, meaning that every finite index subgroup gamma 1 of gamma has finite Galenization, then the group is actually SS rigid. And of course, without FAB, gamma cannot be SS rigid. That's clear, because if gamma is finitely generated and fails to satisfy FAB, then some finite index subgroup can be mapped onto Z, which of course is not rigid, and then gamma is not rigid itself. And another remark is that while this theorem was stated for discrete bounded generation, it actually can, the condition can be weakened and can be replaced, for example, by profinite bounded generation. Another quite interesting application has to do with the congruent subgroup problem. So the standard setup for the congruent subgroup problem is that we look at an algebraic group, G, defined over some number field. Now we fix a set of places, S of K, and look at the corresponding ring of S integers. And we'll let gamma denote the corresponding S arithmetic subgroup. Given this data, we can consider two things. One is the completion of gamma for the topology defined by all finite index normal subgroups. That's nothing but the profinite completion. And on the other hand, so we can consider the completion of gamma for the topology defined only by congruent subgroups. Namely, for every non-zero ideal of the ring, we can look at the kernel of the reduction map mod A. That's what the congruent subgroup is. And in the number theoretic situation, of course, the quotient O by A is finite. So gamma of A is actually a subgroup of finite index. And so we consider this family and complete gamma with respect to this family of subgroups. Of course, the profinite topology is stronger, or at least a priori stronger than the congruence topology. So this gives us the map from gamma hat to gamma bar. And the kernel of this map is called the congruence kernel. Now, it's very easy to see that the congruence kernel is in fact trivial if and only if we have the desired answer to the congruence subgroup problem in the classical sense, namely every finite index normal subgroup contains a suitable congruence subgroup. Now, in general, the congruence kernel is not necessarily trivial. So the congruent subgroup problem is really the problem of computing C in various situations, and in particular, determining the cases where C is finite. In this case, we say that we have the congruent subgroup property. Now, the following theorem was proved by Lubotsky and Platonov and myself. So let G be an absolutely almost simple algebraic group. Now, I need to include one technical assumption, but you don't need to pay attention to this. So it refers to the so-called Margulis-Platonov conjecture, which is almost a theorem. So that's why, so I need to put this to make the theorem actually correct, but you don't need to pay attention to this. So the main part is that the congruence kernel is finite, even only if the profinite completion has bounded generation as a profinite group. In particular, if gamma itself has bounded generation as a discrete group, then C is necessarily fine.
If and only if is only about the profinite completion?
Yes, yes. And I will get back to this in the end of the talk. So at that time, we sort of viewed this result as a sort of uniform approach to the congruent subgroup problem, because there was information from Fritz Grunewald that he was able to check bounded generation for certain quaternion groups using computer. Well, I will tell you what happened later. But bounded generation was used also for other purposes. For example, Shalom and Willis used bounded generation to prove, at least in certain cases, Margulis-Zimmer conjecture on commensurated groups. Bounded generation was also used to estimate Kazhdan constants in certain cases. And for completeness, let me mention that bounded generation for pro-P groups is actually equivalent to their analyticity. So bounded generation has quite a few consequences, and this sort of justifies the interest in that property. Now, the available results created some sort of expectation that higher rank lattices should always have bounded generation. That was our dream project. Now, on the other hand, it was known that rank 1 lattices certainly do not have bounded generation. But the interesting thing is that this dichotomy between rank 1 case and higher rank case is what always happens in the theory of discrete groups, so it's expected. But in this case, we also see a dichotomy between uniform and non-uniform cases. So namely what happened was that over more than 30 years of sort of investigation into bounded generation, no examples of S arithmetic subgroups of anisotropic groups have been found. So let me recall that G is called anisotropic over a field K of characteristic 0 if there are no K rational unipotent elements. Such groups can be obtained, for example, by taking an anisotropic quadratic form, a form that does not represent 0, and looking at its orthogonal group. Or one can take a quaternion algebra and take the group which is defined by elements of norm 1. And this brings us to the following question. Can bounded generation possibly hold for an infinite S-arithmetic subgroup of an isotropic algebraic group? And one can consider different variations of this question, one being the following. As I told you on the previous slides, in all known examples of bounded generation, this bounded factorization of a group always involves some non-semisimple elements, typically also unipotent elements. So on the other hand, so we do know that, for example, SL and Z can be boundedly generated by unipotents, but no one was able to find a bounded factorization where all elements would be semisimple. Okay. So, and this leads us to question B. Which linear groups are boundedly generated by semisimple elements? And that's the question that I would like to discuss. And so we were able to answer this question in joint work with Pietro Corvair, Jean Bourrienne, and Umberto Zanier. Here's the main theorem. So suppose we have a linear group gamma over a field of characteristic 0, and assume that this group is not virtually solvable. It does not have a finite index subgroup, which is a solvable group. Then any possible bounded factorization for that group must involve at least two non-semisimple elements. So in particular, a linear group which is boundedly generated by semisimple elements must be virtually solvable. Okay. Now, unfortunately, it's not a criterion, so one can relatively easily construct solvable finitely generated linear groups without bounded generation, but it becomes a criterion for anisotropic groups. Namely, building on the definition I gave for algebraic groups, we will say that a linear group is anisotropic if it consists only of semisimple elements. And again, such groups can be constructed using division algebras or anisotropic quadratic or Hermitian forms, so they do exist. So, and in this case, we have the following statement. Corollary 1, and an isotropic linear group over a field of characteristic 0 has bounded generation if and only if it is finitely generated and virtually abelian. No other anisotropic group can have bounded generation. And in particular, so infinite S-arithmetic subgroups of simple anisotropic algebraic groups do not have bounded generation. So this basically concludes the survey part of my talk, and then I would like to show you some proofs.
Are you going to come back? Yeah, I want to see the proofs, of course, but are you going to come back and revisit the congruent subgroup property? What this, I guess, is, in your opinion, meaning this is not an approach to prove the congruent subgroup property in these groups, or is it an indication maybe congruent subgroup property fails? What's your...
No, I don't think it fails, and I will get to this at the end of this talk.
Okay.
Yes,
right.
Thank you, Peter, for that question. But now, first, I would like to walk you through the proof of the fact that SLN Z, when n is 3 or larger, has bounded generation. So it's a kind of fun. First, using Euclid's algorithm, one easily reduces an arbitrary unimodular matrix over Z to this block diagonal form by a bounded number of operations. That's a very easy exercise. So to prove bounded generation by unipotents, it's enough to show that every such block diagonal matrix in SL3Z can be reduced to the identity matrix by a bounded number of operations. And here I put these stars in the second row simply because the second row really doesn't matter. So any two matrices with the same first row, they differ by one elementary transformation. If one has bounded presentation, then the other has bounded presentation. And if you're familiar with the congruent subgroup property and the work done by Bas, Milner, Serre, and Menneke, so these matrices were used to define so-called Menneke symbols. And the crucial property for writing the bounded presentation is the following property, which we refer to as bounded multiplicativity of Menneke symbols. So what happens is that if we have a matrix of the block diagonal form, we raise it to the L's power, where L is any positive integer, then it can be reduced to this matrix by a bounded number, namely by 16 elementary operations. Okay. That's a direct computation. There is no reason for that to be true in general, but that's what happens. Okay. Now, this equation represents the effect of one elementary operation. So I multiply the first column by A and add it to the second column. That's what I get. So, and as you see in the right upper corner, I am getting an arithmetic progression. So using Dirichlet's theorem, we can actually assume that this element B is a prime number. Okay. Now we can play actually a similar game with this element C, namely applying Dirichlet's theorem twice and using some computations. We can actually assume that our matrix is of the form where both P and Q are odd primes, and the GCD of these numbers is 1. That's not difficult, but again, it uses Dirichlet's theorem. Now, what's the point of this? So since the GCD is 1, we can find integers m and n so that the linear combination is plus or minus 1. And let me call the first number S and the second number T. The point here is that by Fermat's little theorem, of course, u to the S is plus or minus 1 mod P. So when we raise our matrix A to the S power, then by 16 elementary operations, we can transform it to this matrix. But then we can subtract a multiple of P and get plus or minus 1 in the top corner. And then the whole thing becomes a bounded product of elementaries. Now you can take the transpose and apply the same thing to A to the T. So again, it's a bounded product of elementaries to the effect that A or its inverse is again a bounded product of elementaries. This is how you get bounded generation for SL and Z.
Can I ask a question?
Sure.
Is the 16 step the only thing that doesn't work if you were to do it for SL2? Like what fails for SL2?
Yes, you cannot do this multiplicativity property inside SL2. You need at least SL3.
Okay, thank you.
Yes, thank you for the question. But of course, there are still some questions about bounded generation of SL and Z. Yes, A can be written as a bounded product of elementaries, but can you also put a bound on the entries of those elementaries? For example, if we have a reasonable bound on the entries of A, can we have, let's say, a polynomial bound on the entries of the elementary matrices that occur in the factorization? So the expected answer is actually no, but we have not been able to prove this. You can also ask, well, can we do something like this over a general, let's say, Euclidean ring? Let's say without using Dirichlet or something like that? And the answer is no. Again, very early in this development, van der Kallen showed that there is no bound on the number of elementaries for the group SL3 of C box X. Well, what he used was the fact that C has infinite transcendence degree over Q, which tells us that if you look at K2 of C, there are arbitrarily long products of symbols that cannot be reduced. Using this, one can construct pretty explicitly the matrices in SL3Z, which are given by product of elementaries, but these products cannot be reduced to a smaller number. This is how it works. But the question still remains open when you don't have infinite transcendence degrees. For example, if you have Q box X or Z box X. So that's a positive result. So when we do have bounded generation, now let's go to the main result, which is actually negative. So let me remind you of the statement once again. So suppose we have a linear group over a field K of characteristic 0, which is not virtually solvable. Then any possible bounded factorization for gamma as a product of cyclic subgroups must involve at least two non-semisimple elements. In particular, if a linear group is boundedly generated by semisimple elements, it must be virtually solvable. So that's the theorem. Now, we start by doing two reductions. One is we use a specialization argument that shows that if there is a counterexample to the theorem over any field, there is also a counterexample over Q bar. Okay. And this tells us that it's enough to consider only the case where our group is over Q bar. That's the first reduction. The second reduction is also easy. So now assume that gamma is not virtually solvable. Then one can take its Zariski closure and divide by the radical of the Zariski closure, of the connected component of the radical of the connected component of the Zariski closure. And this reduces us to the case where the Zariski closure of our linear group is, or rather its connected component, is a non-trivial semisimple group. That's the second obvious reduction. Well, but the meat of the argument is really the statement that I will show you on the next slide. And it only operates with the eigenvalues of elements. So suppose we have a matrix gamma. By lambda of gamma, we will denote the subgroup of the multiplicative group, which is generated by all eigenvalues of gamma. Okay, and then the key statement is the following. So suppose we have a bunch of matrices in G ln of Q bar. Now we want to assume that they are semisimple, but in fact we can allow one exception. So let's assume that we have a collection of matrices which are semisimple with one possible exception. And suppose gamma is another semisimple matrix. Now assume that gamma has an eigenvalue lambda, which is not a root of unity, and which satisfies the following condition. So the cyclic subgroup generated by lambda is disjoint from the product of the subgroup generated by the eigenvalues of other elements. So in other words, suppose our matrix gamma has an eigenvalue which is independent from the eigenvalues of all other matrices. In this case, we prove the following, that the intersection of the cyclic group generated by gamma with the product of the cyclic group generated by all other guys is finite. And then, of course, the group generated by gamma cannot be inside that product of those cyclic subgroups. That's how it works. And this statement is quite general. We hope that it can be used for other questions involving linear groups, not only bounded generation. Now, in order to conclude the proof of the main theorem, now we need to show the following, that suppose we have a bunch of elements in our group gamma. We want to construct another element, semisimple, whose eigenvalues are disjoint from the eigenvalues of the given elements. And this can always be done, and that's a consequence of our results with Gopal Prasad of the existence of generic elements in arbitrary Zariski dense circles. That was proved a while ago, and since then there were different variations. So that's basically the proof of the main theorem. So now let me focus on the key statement. So the proof relies on the following remarkable fact, which is Laurent's theorem, that states the following. So suppose omega is a finitely generated subgroup of the product of q bar taken n times. And suppose sigma is a subset of omega. Then the theorem tells us that the heuristic closure of sigma is a finite union of translates of algebraic subgroups of the torus.
By the way, that theorem holds without assuming that they are algebraic. Why did you have to make that first reduction? This is Lang's GM. It's much more. I guess you can always specialize in that theorem too, but
so maybe it's not necessary. So, but that's the way I sort of learned about these things. So
it's true. I think Laurent proved it in that form, but there are even bounds for the number, for that finite number, and they are actually there's an absolute height Schmidt subspace theorem which allows you to get uniformity over all number fields, and then it's specifically asked where you don't put them in any number field. So I'm just
thinking that maybe the first reduction is not necessary, but the thing is that until I started talking to Xavier, I didn't know about the theorem, to be honest with you. So, and when I learned this, so I learned it in this form, so we decided to put it.
No, it's this is Lang. I mean, Laurent proves this conjecture of Lang called Lang's GM. That's what this is.
Yeah. So anyway, basically what it says is that if there is a polynomial relation that holds on sigma, that this relation somehow reduces to relations of multiplicative type. So algebraic subgroups of the torus are of course given by characters. And then we also need to translate. So I will refer to these relations as relations of multiplicative type. Anyway, so this theorem plays the crucial role, and let me explain to you how we use it. Now, let's consider only the case where, let's say, all elements are semi-simple. If they are semi-simple, then let's go ahead and diagonalize them. So we find these matrices G so that they diagonalize gamma and all the gamma i's. And then the idea is to first introduce R times n matrices, variables, x11 through xrn, and in a way that will correspond to the eigenvalues of those elements. So what we do is we form the following product. As you see, when we replace the variables with the powers of the eigenvalues, we'll be getting precisely the elements of the product of cyclic subgroups generated by gamma 1 through gamma r. Okay, so we will refer to this product in the square brackets as sort of generic element of the product of the cyclic subgroups. And let P be, let's say, just the 1, entry of this matrix. I take 1, 1 because I assume that the lambda 1 eigenvalue is my lambda. Okay, let's consider the set of elements so that of integers so that the m's power of gamma is inside the product. Now remember, we want to prove that this J is finite. Okay. In any case, for any m in J, we can find integers a1 through ar so that gamma to the m is the product of the powers of these elements. Now, as a consequence of this and my definition of the polynomial P, so we have this relation. Okay. So for each m in J, we have this relation. Then what we do is, of course, we consider the set of these elements. Okay. So the m's power of lambda itself, and then coupled with the corresponding powers of the eigenvalues of the elements gamma 1 through gamma r. That's going to be our set sigma. Of course, it sits inside that finitely generated subgroup of the torus. Okay, and now assuming that gamma is infinite, but remember the number of translates is finite, so using the pigeonhole principle and using the description provided by Laurent's theorem, what easily shows that some power of lambda is necessarily inside the product of these subgroups, which of course violates our assumption and complete the proof. So the proof is quite easy if you know Laurent's theorem, which I didn't until recently. And now, so now we know that if we have an S-arithmetic subgroup of an anisotropic group, then it doesn't have boundary generation. On the other hand, the congruent subgroup property is known for many anisotropic groups, okay, including, for example, spinor groups and so on. And each such example gives us an example where the profinite completion has boundary generation as a profinite group, but gamma itself doesn't have boundary generation as a discrete.
Can you say a word? I mean, so these other cases of compact or anisotropic, as you call them, cases for which we know the congruent subgroup property, like spinor groups or maybe some orthogonal groups, what is the tool to prove it there?
Well, there are three tools. I'd be happy to sort of talk more about this. One tool is to use actions. I don't think I can sort of formulate this easily, but
I mean, is there? You're not using unipotence. It's completely different.
Well, yeah. The way Kneezer proves it is the following. Suppose we have a spinor group. It acts on a sphere.
Mm-hmm.
We can fix a point on the sphere and consider the stabilizer. Okay. So suppose our group is G and the stabilizer is G of X. Then the main thing that you prove is that on the level of the congruence kernels, the map from the congruence kernel of G of X to G is surjective. And on the other hand, if you look at that stabilizer, there is an element that acts trivially. For example, if you look at the matrix -1, 1, 1, 1, it acts trivially.
Mm-hmm.
And once you have a single element that acts on the congruence kernel trivially, then the normal subgroup generated by that element also acts trivially of the group of rational points. Mm-hmm. But in this case, it's the whole thing. So that's how you prove that the whole group acts trivially, so the congruence kernel is central and therefore is finite.
Does the rank have to be quite big, or is it just rank 2?
Yes, the rank, in order to have some theorems that certain elements are represented, you need to have the rank at least 5 for orthogonal groups.
Okay, thanks.
It doesn't work for 4 or 3.
And in particular, yeah, and doesn't work for your quaternions, right?
It doesn't work for quaternions. Although there is another class of groups that includes, for example, the favorite group of many people, which is E8. So one can prove the congruent subgroup property for E8 by using a different type of argument. Namely,
there's a compact form of E8.
Yes, compact form of E8. I did this like 30 years ago. Okay. So, but still, I mean, the whole proof is not published, so I should do it sometime. But the thing is that E8 becomes split over a quadratic extension. So there is a torus inside, which is the product of one-dimensional orthogonal groups. And then each root subgroup is actually, which is a quaternion group, so it is defined over the base field. And of course, we don't know the congruent subgroup property for three-dimensional groups, but each of these can be embedded into a bigger group inside our group, which is of classical type. And then you know the congruent subgroup property. So in other words, what you show is that if you look at the three-dimensional root subgroups, then each of them gives you sort of finite congruence kernel. And then the whole group is in some sense generated by those. Using that thing, you can prove that, you know, the congruent subgroup property holds also for E8, for example. But what we cannot get our hands on is the case of three-dimensional quaternionic groups. That still remains a problem. Okay, and then, so where do we go from here? So the result was negative. Should we forget about groups with boundary generation? So I don't think so. And first of all, it would be nice to have this property for all isotropic groups, because as Shalom and Willis showed, this can be used for other things like Margulis-Zimmer conjecture. But another thing is that the techniques we developed to work with groups with bounded generation work under weaker assumptions. So let me mention these assumptions. One can show that SS rigidity and the congruent subgroup property follow from the following weaker assumptions. Namely, for a group gamma, that's denoted by gamma n, the normal subgroup generated by the nth powers. And then we can consider the following condition. So the polynomial index growth, let's assume that the size of these quotients grows polynomially in n. Okay. First of all, if gamma has bounded generation, this property obviously holds. Okay, so it's a really weaker condition. In fact, we can make it still weaker and consider the following. Let's consider the same condition, but require it not for arbitrary n, but only for n of the form some fixed integer times an arbitrary prime power. Okay, we call it PG prime. The point here is that, as I showed you, even for SL and Z, bounded generation requires some number theoretic input, like, for example, Dirichlet's prime number theorem. Now, this property PG prime can be checked by just computation with commutators without using any number theoretic input. Also, in fact, this property is open to computer-based verifications. And I asked some knowledgeable people to check this for quaternionic groups. And as far as they could go, it does hold for quaternionic groups. Okay. So it should be some indication that, you know.
You mentioned, and I see Alex is here too, he might remember. You mentioned Grunewald. Did he, you know what he checked on the computer?
No, when I talked to him, that was my last meeting with him, unfortunately. So he showed that he was not able to do that. So what he did was he checked the indices of the commutators of the congruent subgroups. Now, from my viewpoint, these indices give you the analyticity of the pro-P completion. Okay, this can be shown. So his computation with some input from, you know, what I can prove shows that if we take these quaternionic groups, that in certain cases we can guarantee that the pro-P completion is p-adic analytic. But it's not strong enough to prove the congruent subgroup property. So in other words, so we have some hope in this PG prime condition. So let me state the problem, prove that in the higher rank case, when we have an arithmetic subgroup and the S rank is at least 2, then gamma should satisfy PG prime. That's where the focus should probably be. And another interesting question is about amalgams. Now, if we look at the group SL2 of Z of 1 over P, this group is known to be a non-trivial amalgamated product. Namely, by SER, it is the amalgamated product of two copies of SL2Z, meaning virtually free groups, amalgamated along a common subgroup of index P plus 1. Okay. And this group, of course, has a sort of an anisotropic cousin. And this group, of course, has bounded generation. But let's look at the anisotropic cousin. So we can take, for example, the algebra of usual quaternions and localize two odd primes, P and Q. And look at the quaternions where the coordinates belong to that localized ring. Now, this group also has a very similar presentation, but according to our theorem, it does not have bounded generation. So one would like probably to know what is going on. So in other words, one would like to see a sort of verifiable condition for amalgamated products to have bounded generation or satisfy this condition PG prime. Now, I must say that Rigidity and Fujiwara actually gave necessary conditions using bounded cohomology for amalgamated products to have bounded generation. But these conditions do not explain the phenomenon I talked about on the previous slide. So, and let me finish with a very general and vague question. So, in fact, up to now, all examples of groups with bounded generation, this way or another, are related to arithmetic groups. So one would like to know if this is really the case, so that namely all examples of bounded generated groups involve S arithmetic groups this way or another. And particularly, we are interested in those linear groups that are non-trivial amalgams. Thank you. And this is all I have for you today. Thank you.
All right, let's all unmute and clap.
Thank you very much.
Yeah, I don't think it's negative at all.
Yeah.
It's a fantastic application of a very deep dive into theorem, by the way. I mean, it's not this requires a full force of the Schmidt subspace there.
No, I'm really happy that the question has been resolved, because it bothered me for quite some time. Now it's resolved, and we need to sort of explore different directions.
So the way you're talking, you believe the congruent subgroup property in this last example, say in problem 2 here, you believe PG primed is true? Is that what you suggested?
Yes. So it really has to do with analyticity. So it's a stronger version of analyticity. So if you just say, let me go to the previous slide.
So let me just ask you this. Of course, Zania would know this better than anyone. The fact that you, in the proof of Laurent's theorem, you can give bounds for the size, but not for the number, but not for the size of the elements. That's not useful. That doesn't impact at all this PG primed.
This I don't know. Yes, that's a good point. So this needs to be looked at. But so coming back to the PG prime, see if you take m equals 1, that the polynomial index grows for the powers, for the quotients modulo p to the alpha, really gives you that the analyticity of the pro-p completion. And like I said, the analyticity can be checked experimentally in certain cases. So therefore, I believe that there is some evidence that this condition PG prime may hold also in the anisotropic case. So that's the.
You said that there's some condition for this amalgamated product to ensure bounded generation. And of course, it can't apply in this quaternion case. What kind of condition is it?
Yes, the condition is that it says that under certain conditions, there is no bounded generation. And
okay.
Sorry for the confusion. So namely, it says that the space of these quasi-characters, so bounded to homology, is infinite dimensional. And the condition is the following. So suppose we take gamma 1, and then we take double cosets with respect to gamma naught on both sides. So take the double cosets of gamma 1 modulo gamma 0 on the left and on the right. If the number of cosets is at least 3, then they can show that this group doesn't have bounded generation.
So they're not able to give any examples of using this, like maybe instead of taking P and Q, if you look many primes,
No, by the Briochati composition for SL2, in the quaternionic case, this number is always 2.
I see. Mm-hmm. Okay.
That's precisely because the subgroup that you amalgamate over is, when under the reduction, it's really the Borel, so it's a Vahori. Mm-hmm. And then by the Briochati composition, in this case, the number of double cosets will always be 2. So their condition doesn't apply in this case.
Yeah. Andrei, does it says anything for the uniform lattices about the normal closure of a conjugacy class? If you take a conjugacy class and you look at the subgroup generated by that I think Dave Morris showed in his paper that it is what he called finite width or something like that, that every element is a bounded number of conjugates.
Yeah, that's another finiteness property. You're absolutely right. So I don't know at this point.
So you don't know anything about co-compact lattices, if any of them has this property or any conjugacy class. And
but that's another important thing. So that the normal subgroup generated by an element is a bounded product of the conjugacy classes, right? So, but so far I know nothing about that.
Nothing. There are no examples either way, right? for the co-compact.
Right. The hope is that one can use this key statement also maybe to analyze this.
Mhm.
Because you see, after all, we're operating here with the products of cyclic subgroups. Why not operate with the products of conjugacy classes? That's also possible by more or less the same kind of argument. But that's a good point. We haven't done it yet. But maybe someone can try. Because ultimately, everything, when we reduce those polynomials, so we operate with eigenvalues. Maybe this something can be done, but this hasn't been done yet.
I have a question. Thanks. That was a wonderful talk. I wonder about quantitative versions of this non-bounded generation. If I take some semi-simple elements and I try to count how many elements are boundedly generated by them, I would imagine that's much. You might guess it's vastly smaller than the growth of the whole group. Can you prove some quantitative estimate from your argument?
No, actually, so that's the way I tried to disprove bounded generation for a long time. So, of course, if you take semi-simple elements, when you raise to the powers, the entries grow exponentially. And intuitively, it's clear that you cannot cover the whole group. But the question was, so if there are certain cancellations, so what can happen? And then here, I mean, came up with that idea, so that, you know, even if there are cancellations, then still something holds for eigenvalues. So actually, it's an excellent question, and that's the way I tried to prove that there is no bounded generation, but I didn't succeed.
Andrei, may I ask? I guess probably you cannot, but I just wonder. I remember that at the time, the work I did with Raghunathan and Shachar Moses about U elements really started from a mistake of mine. Somehow I thought that bounded generation, that it's necessary in a bounded generation to have what nowadays we call a U element.
Yeah.
In fact, that's what you are proving now for the linear case, but using eigenvalues.
Yeah.
Now, I guess you cannot see a way to prove in general that let's take an abstract group and assume it's a bounded generation and not virtually solvable, and let's say even residually finite. I mean, can you see a way to prove that that it must contain U elements?
Well, our techniques are all linear, so if you have enough representations, that may be, but not immediately. But thank you for the question. So maybe I should think about that. But even if you look at the paper, so even allowing one unipotent is a kind of pain because you need to eliminate certain variables and so on. So one would expect the theorem to be that every bounded generation should contain at least 4 non-semi-simple elements, because for 5 it already doesn't work. So, but even allowing 1 is a kind of pain. Maybe 2 can be handled, but we don't see any way to improve this to 4 elements at this point.
Kind of interesting because historically, I guess the first proofs of the superrigidity or arithmeticity were when you have unipotents.
Right.
And then the hard case was when you don't. And so somehow, in this case, the hard case, it goes the other way.
Yeah, I mean, in this case, you simply can't. That was a kind of surprise.
You have to be careful. I mean, like superrigidity went the wrong way also, right? With Corlett in SPN 1. So one has to be careful about what one conjectures, yeah, I guess. Yeah. Amazing.
But thank you for all your questions. So we'll look into those.
Alex stayed up late for you. Must be. What's the time there?
It's after midnight, 12:30.
Oh,
But it was worthwhile to wait.
thank you very much, Alex.
But I had difficulty to get into the talk because there was a question that I had to solve at midnight. What's the number with 3 digits that equal to the cube of the sum of it?
I sent you the solution. Don't pretend you didn't.
Well, eventually I solved it before I got your email. But why you do it? Why you not? Why you think that if you allow everyone to get into the talk, then
It was put,
people who will come?
I think it was put right at the beginning, right? I don't know why. But I must say, I was late for a talk too. And it was midday, and I was like, what?
All right, if there are no more questions, let's all clap again. Thank Andrei for a great talk.
Thank you very much for your attention. Thank you. And for your questions and for your input. I appreciate this.